In this video, we're going to talk about thermodynamics, including the first law of thermodynamics, which describes changes in energy, work, and heat. So the first law of thermodynamics states that the total change in energy for a system is going to be equal to the heat transferred to it plus the work done on the system or by the system. If you have work done on the system, that means that you're going to have a positive value for work. If you have heat added to the system, that means you have a positive value for Q, or heat transfer. So when we're talking about work in physics, we're not talking about work as in what you never do if you enjoy your job. What we're talking about is the physics definition, which is force times the distance over which it's applied. And when we're talking about chemical systems, a lot of times when we're talking about gases during explosions or something, you have a change in volume. So the work could also be defined as negative P delta V. So the pressure against which it's expanding or contracting. If the system is expanding, it's going to be doing work on the surroundings because it's going to be pushing out and making other things move. So if you have a positive volume change for the system, that means it's doing work on the surroundings and would have a negative value for Q. So that's why it's negative P delta V. All right, so just to kind of reiterate what I said, if we just graphically represent that, if you have heat being transferred into the system, that means Q is going to have a positive value. That would represent an endothermic process in which the system's gaining energy. If work's done to the system, basically you're compressing something where work is being done, then W is going to have a positive value. However, if you have heat being released, like in an exothermic process, or you can have work being done by the system. So if you think of an explosion, it's pushing out, it's doing work on the surroundings, and it's releasing heat. All right, so the total energy change for an exothermic explosion is going to have a negative value for a delta E because both Q and W would be negative. So we've been using Q to describe heat change when we're talking about calorimetry. Q equals Cm delta T. That's how we measure how much energy is transferred between objects. All right, so for the most part, you can pretty much consider that to be equal to something called the enthalpy change. Now, the enthalpy change represents the change in heat content of the system. Right. Excuse me. So, and that applies when it's at constant pressure, which most reactions we do are against the constant pressure, so you don't really have to worry about it. So you can think of delta H as essentially being the same thing as the Q that we've been learning about this year. And since the total change in energy is equal to the change in enthalpy, or essentially Q, plus the work, work is usually pretty small. If you're talking about a system where there's no expansion or contraction, it really doesn't have any impact. So in that case, you're going to be looking at the total change in energy being equal to the enthalpy change. All right, so again, change is the final minus the initial values of the components. So if you have a negative value for delta H, that means the system released energy. And if you have a positive value, that means it's gaining energy. That would be endothermic. If it loses it, it's considered exothermic. Graphically, what this would look like. This is an endothermic process where you can see that your reactants have a lower heat content than your products. So there's a positive change to be endothermic. Now what's missing here is usually during a chemical reaction, you have bonds being broken. That requires an input of energy, but you usually also have new bonds being formed. So what's not being shown here is usually there's going to be a little hump here where you have, energy being absorbed for this part, bonds breaking or things being pulled apart, and then you're going to have a little bit of a release of energy as your products form. And the exact opposite is true for exothermic processes, where your reactants, still, they would have a negative value for the change in enthalpy because they're losing that heat energy. Again, it's not showing any energy being put into break bonds, which is usually what you see. For example, this would be an example of maybe condensation, where you don't have any bonds being broken, but you have new bonds forming as it condenses. So typically during a reaction, though, you would see some activation energy required for the process. All right. So here's an example of a problem you might get about energy change during a reaction. So if we know that the heat of combustion for glucose is negative 2803 kilojoules per mole, what that means is that for every mole of glucose that you burn, you're going to release that much energy. And when I see the negative sign here, I like to just attach the word release to it. That way you don't get confused. And then at the end you can think about release versus absorb, where release is going to give you a negative change in energy and absorb will give you a positive one. So that way you don't lose signs in the process. So in this, it's asking us to calculate the delta H, or the change in energy heat content, for the reaction of 6.5 grams of carbon dioxide is formed. So here we have the reaction. Since the delta H is negative, that means we're going to be producing energy or releasing energy. So energy is a product. So we put the 2803 on that side. If it was a positive value for delta H, we would put it on the reactant side. All right. So start with 6.5 grams of carbon dioxide. So we know that's what's being formed. We know that 1 mole of CO2 is 44 grams, and that it releases 2,803 kilojoules for every 6 moles of CO2 that gets produced. So that's 69.1 kilojoules released, and therefore we would say it has a negative energy change of 69.1 kilojoules.